Let's start with a sketch of this problem. So here's the situation. You have a parallel plate capacitor, so I have two separated plates. Okay. Two separated plates. One of them is charged up negatively. The other is charged up positive. And there's an electric field in this region between these two plates. Now we know the direction of the electric field is from positive to negative. So I have an electric field that's uniform in between the two plates, points like so. Okay? And we know the electric field strength. It's 20,000 volts per meter. We also know the spacing between the two plates. We're told that the spacing is 1 millimeter. 1 millimeter is 0.0010 meters. Okay? Electric field is uniform between here and here. Electron is released from rest at the negative plate, and the question is, what is the electron's speed at the positive plate? Well, if an electron is released from rest right here, okay, the electron is going to experience a force opposite the electric field. So the electron feels a force in this direction. The electron will accelerate from here to here. Now there's a couple of ways we could solve this problem. One way we could solve this problem is to say, oh look, the electron experiences a force, we can calculate an acceleration, we know the distance, and so we could calculate the speed. But there's a more straightforward way to do it in this problem. And think about this. As we go from this plate to this plate, okay, the electron moves from here to here, it's moving opposite the electric field. If I'm moving opposite the electric field, I'm also going up in potential. If we say the potential at this plate is 0 volts, okay? At this plate, the potential difference is just going to be equal to the electric field times the distance, because the electric field in this region is uniform. So the difference in potential is just 20,000 volts per meter times the distance of 0.0010 meters, and so I get a difference in potential of 20 volts. So if it's 0 volts at this plate, it's 20 volts at this plate. And so the electron has gone from 0 volts to 20 volts. It's accelerated through a potential difference of 20 volts. Now, we're going to think about this in terms of electron volts, which is a very handy unit of energy. This tells us that the electron has lost 20 electron volts of potential energy. It loses 20 electron volts of potential energy. Well, if it's losing potential energy, it's gaining kinetic energy. How much kinetic energy does it gain? 20 electron volts. So it starts with a kinetic energy of 0 electron volts. By the time it gets here, it's got a kinetic energy of 20 electron volts. Then the question is, what speed does this correspond to? Well, if we're going to do a calculation of speed, we have to convert the 20 electron volts into joules. Okay, we've got to convert this to joules. And remember, 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. And so the electron finishes with the kinetic energy of 32 times 10 to the negative 19th joules, because it's got 20 electron volts. So the electron's final kinetic energy is this. Well, that kinetic energy, of course, is just equal to 1/2 mv squared. Once we're there, our solution is actually quite straightforward. We can say this. For the electron, 1/2 mv squared is equal to 32 times 10 to the negative 19th joules. Well, the mass of the electron is 9.1 times 10 to the negative 31st kilograms. And I wrote this out because I want to notice this. The energy is 32 times 10 to the negative 19th joules. The mass is 9.1 times 10 to the negative 31st kilograms. So this is a lot of kinetic energy for the electron given its mass. And so we expect the speed to be quite large indeed. As a matter of fact, we can just take this. We know everything in this relationship except for the speed. And if we solve for it, we get a speed of 2.7 times 10 to the 6th meters per second. That's just shy of 1% the speed of light. And so we can assess our result. We expected that this was a big amount of kinetic energy for the electron. We expect it to move quickly. In fact, it does move quickly. 1 electron volt is a tremendous amount of energy if you're an electron, and so we expect it to be moving rather quickly. And so this answer matches the way we know the world works.